Morning all. In the previous lectures that I've taken, we have already talked about the integration of smart manufacturing in AM, and in the last session I have already talked about this how VAM CMTs work, the process and the process is working with VAM CMT, and how the sensor integration, feedback mechanisms, and collection of data, and this integration of ML, digital twins. So all the things we have already completed. So we have already completed the seven factors of smart manufacturing, that is process monitoring, digital twins, data analytics and machine learning, industry 4.0 integration, and industry 5.0 also. And that automation and robotics part, we have covered sustainability and resource efficiency and mass customization. So these things we have already completed. So now today's lectures about the materials fabricated using VAM CMT. I've already talked about the how VAM CMT works, but what are the materials that can be fabricated using VAM CMT, and what are the problems occurred, and what are the sensors we can use, thermal imaging cameras we are using to mitigate these anisotropy defects and all. So today's session will start. Yeah. So a recent application that have come through fabrication of VAM CMTs, prototype subsea bonnet. You can see here. This is made by Robert Graham. This is a welding group innovation head. So this is a complete product that is fabricated under one roof, under a single roof we have completed. Traditionally it is taking too much time, like with conventional manufacturing processes, it is taking almost 3 months of time to arrive through conventional supply chain, because we have to fabricate different parts and then assemble it, and using uh, it is taking 2 or 3 months to arrive at a single roof. So that increases the carbon footprints. So what is the advantage of fabricating through VAM CMTs? We can fabricate the whole component in one go, under one roof, with lesser time, and we because of the high deposition rate that CMT has. And what major we are reducing is we are automatically reducing the carbon footprints, that is almost 60%. So someone has he has calculated that 70 kg of material has been deposited using CMT. That deposition rate is here 6.5 kg per hour. That is very high. So at this deposition rate, this much kg of material has been deposited, and 60% of approximately 60% carbon footprints had been reduced. So this is a very good initiative of reducing carbon footprints by fabricating by different like conventional processes. We can adopt wire arc additive manufacturing through CMT, so that we can reduce these carbon footprints. This is the major problem in today's today's scenario. So these are the typical application with VAM. You can see wing spar made of titanium, landing gear. This is made of titanium. So Cranfield University, you may be heard about this. This university is working with VAM 3D. This is a company that is started with a PhD scholar. A PhD scholar has made a startup, and he only made this company, well-renowned company, VAM 3D. So he's fabricating all the 3D components of different materials like aluminum, stainless steel, this titanium alloy, and this inconel alloy. So all the materials there he's fabricating, and he has a very good team. So he's using Fronius machines like robotic CMT coupled with the KUKA robots. So many applications he has done it, like TI6AL4 vanadium wall structures, this titanium landing gears, wing spars, and You can see this is the world's first 10-meter class high strength aluminum alloy connecting ring of heavy duty carrier rocket by additive subtractive WAM technology. So you can see the surface is very smooth because we have like deposited through WAM, like wire arc additive manufacturing using CMT, but after that the subtractive manufacturing is also taking place. So that's why the surface is smooth as compared to this. You can see this is having some undulations. This is also having some undulations. This is the as fabricated component. This also, so this is as fabricated component, and this is the finished component after subtractive manufacturing. You can see the smoothness of the components. So these are the typical applications using WAM. So this I have already covered this WAM CMT in the last lecture. How CMT, uh, how the CMT power source is helping for good component WAM structures. We can use other power source also, like welding power source, that is GMW, GTW, pulse, this PAW, but uh, researchers and the experimental results tells about that the CMT CMT has many characteristics over these threes, like it has high deposition rate, it has low heat input, um, and due to that low heat input, the thermal gradient issues are not having that much problem. The delamination problem is not there in CMT, and like many other problems can be mitigated using this typical power source only. So using WAM, using CMT, we can fabricate a WAM component better as compared to the other like GMW and GTW process. So WAM we already know that is main characteristics is high deposition rate, very economical, and shortened lead time. We can fabricate a large metallic components using moderate complexity. You can as fabricated component after the fabrication, we can go for subtractive manufacturing, and we can achieve a near net chip product. So this is the typical schematic diagram. This I have already discussed in the last lecture, so I'm skipping this. So how this layers are implanted and the inner layers. This inner layer concept is important because with different materials we form different microstructures during this inner layers. So L1, L2 is the interlayer that we are depositing, and L1, 2 is the inner layer formed during the combination of the two layers. So this is also known as heat affected zone. You can tell about heat affected zone, and like it's a weakest zone. The delamination problem occurs from here only, and the coarse microstructure micrograins are visible here only. So this is the weakest zone. So we have to um, have a very good equiaxed or columnar grains in that region, in this region, so that we can strengthen the WAM component. So this is a basic introduction of additive manufacturing. I have already told in the last lectures, like there are 7 families of additive manufacturing, but we are focusing on directed energy deposition because and in directed energy deposition we have laser method, we have electron based method, and we have arc based method. So with welding power source we are focusing on arc based method, and in arc based method we are adopting WAM technology, that is layer by layer additive manufacturing using welding power source. So this is the basic definition. Like WAM process is one of the metal additive manufacturing technique. Its filler wire is melted with help of electric arc, and then melted metal droplets are deposited layer by layer along the planned path to form a product. So these are the sources: GMAW, GTAW, plasma arc welding, and CMT. So basically, researchers are focusing on this only, cold metal transfer based power source, because of many advantages and the very less porosity, and a bulk component can be fabricated using CMT, and the reduced anisotropy problems also. So advantages are high deposition rate, cost-effective method, suitable for large-scale metal parts, material efficiency, near nature product, and repair and refurbishing capability. So this is very important. Repair and refurbishing capabilities nowadays, like if we are fabricating a blade of turbine blades, so the problem of having some pitting corrosion, like some problem is there to in the blades itself. So how we don't want to like um, discard that blades, so we can go for repairing refurbishing. So CMT with VAM component helps in this repair and refurbishing capabilities, so that we can reuse that blade in for the other processes also. So this is the classification of VAM. VAM we have known as GTW, we can use GMAW, CMT, and PAW. So what's the major differences? GTW we already known, it's a non-consumable electrode, and nowadays GTW is also, we have an advanced GTW process, that is a tip-tick process, in which we don't have to feed the filler wire manually. So it is automized, and we have the Fronius or ESAB, yes, they have launched that tip tick process. So in which the wire is also automated, and we have a cold wire feeder, external cold wire feeder, through which the wire is being fed at 45-degree angle, and the tungsten electrode is making that arc, and the wire is coming and melting it. The wire is melting and depositing. So that is also automated nowadays. So for fine process, we can use automized GTW, but it has some limitations also, because it has a very low deposition rate. Low means like 1 to 2 kg per hour. But with CMT, we can achieve approximately 5 to 6 kg per hour maximum. And with GMW is a it's a consumable by wire we are using. Deposition rate is higher, and disadvantages, main disadvantage is its poor weld arc stability and large spatter. Because of this poor arc stability, we are finding out that porosity levels are very much increased in the softer materials like aluminium. If we are fabricating aluminium alloys, aluminium single wall structure of VAM component, by GMW process, we got that higher levels of porosity is there, and there is a problem of this density. So that density is so much reduced as compared to the parent material. So there is a problem of this porosity defects. So large spatter is also not needed in this GMW process, in this VAM process. So if the large spatter is there, the weld aesthetics and the single wall structure aesthetics is not that much good. So that's why we are not adopting GMW process. Rather, we are using CMT. CMT is an advanced version of GMW. We are just optimizing the wire movement. In this GMW, we know that Lorentz force is actually responsible for the droplet detachment and droplet detachment to the melt pool. But with CMT, we have the oscillating wire mechanism that is very much responsible for droplet attachment. And at the time of that filler that liquid metal touches the melt pool, at that time the short circuiting happens, and that the time of short circuiting, the voltage and current has been reduced, so that the liquid metal that is formed at the tip of the wire is being deposited to the melt pool, um, with very low heat input, because at the time of short circuiting the current and voltage has been reduced, so that the colder version, like lesser heat input droplet, has been detached. So that's why the lower heat input concept is there in CMT. It is actually like two-third of heat is only going to the melt pool. So as compared to GMW, it is two-thirds of the heat is required for deposition at the same process parameters. So we have reciprocating consumable wire. Typical deposition rate is this. Maximum we can reach more than this also. Advantages is less or zero spatter with low heat input. Better arc stability we are getting with CMT. So the stability is we are getting better stability. So we are assuming that we are practically we have made it. If we are fabricating aluminum alloys, so we are having a lesser porosity, and we are typically getting 90 more than 97% of the um, density that is commercially available with the commercial materials. So with the same density, almost same density, we can fabricate it. And this is PW, the non-consumable electrode we are using, feed mechanism separate system. Typical deposition is this much and wire torch required. So PW is not that much in the trend. So we are for VAM process, we are only adopting CMT, or if we want a very precise thing, we can go for advanced GTW, not the conventional GTW. We can go for tip-tick mechanism or advanced GTW, that is automized. So this is the comparison of some representative AM processes. So if we are considering powder and wire, these are the two raw materials that are used in additive manufacturing. We are having laser, SLM, SLS, TLF. So with wire we have VAM and EBF. So these are the layer thickness of respective processes, and these are the deposition rate. So VAM has a very good deposition rate as compared to laser and all. It's like minimum 1 gram per minute, and we have 12 gram per minute deposition rate. Dimensional accuracy is a major problem with VAM. You can see here dimensional accuracy plus minus zero point 0.2 mm. That is the outer surface roughness that we are having. Or dimensional accuracy means how much accurately we are forming the single wall structure or multi wall structure or intrinsic components. So this zero point 0.2 mm tolerance or dimensional accuracy problem is there, but you can see with laser it's very fine. The outer surface is very fine. Like we don't need extra subtractive manufacturing with laser, but laser processing is also a costly process, because of these powders are costly as compared to wires that we will discuss in the later slides. You can see here the dimension accuracy is very much less as compared to VAM. And you can see the surface roughness, 200 microns is the surface roughness, and this is 1 or 2 microns the outer surface roughness. So this is very much good as compared to VAM. But VAM has higher deposition rate, and like modern complexity you can fabricate with the VAM process, and carbon footprints we can reduce in the single roof. So this is the basic diagrams. This is D is, I think this is, yeah, VAM fabricated component from the Cranfield University. I told you Cranfield University is very much working in the VAM. They have a VAM 3D company also. So they have fabricated different types of components with different materials also. So VAM happens to be in the middle, like with the moderate deposition rate and part size and the moderate complexity also. So that we can achieve with VAM. So this is the process, how the process is started. We have to start the arc, pre-welding shielding gas, we have to switch on the arc starting, then layer deposition on substrate material, then finishing the deposition, post shielding gas on for cooling the systems. Then after deposition, we have to cool the design required for interpass temperature. So this is the first layer of deposition. So after first layer of deposition, we need some cooling time, or we can give some dwell time, like 30 seconds of dwell time to maintain the temperature at a constant rate. Like for after first layer of deposition, if we wait for 30 seconds, suppose the temperature reaches around 200 degrees Celsius, then the second layer is being layered off, then the second layer is deposited over the first layer. Um, so that that interpass temperature is around 200 degrees Celsius, and then after depositing the second layer, the again the temperature has been we have to wait for 30 seconds to give the dwell time, and the temperature reaches 200 degrees Celsius, then we can put the third layer. So after that we can give the next layer deposition, and then if the required size is reached, we can end the process. Or if we are we want a more height component, like we have achieved 2 mm and we need 10 mm, then again the process is repeated, and the same process is repeated many times when we are completed the height of the component. So heat calculation problem, the heat input is the for single wall structure or a 2D component, we are using eta Vi by S. So volt eta is the 80% efficiency we are taking for GMAW process, GMAW machine, CMT machine. We are taking the thermal efficiency to be 80%. V voltage and current and welding speed is the input process parameter that we can control from the that we can control everything to get the heat input in joules per mm. So, if we are fabricating a 3D component like multi-wall, multi-track systems, then we assume like we have a volumetric efficiency. So, volumetric heat input. So, heat input of AM is joules per mm cube. That is energy by volume. That is energy volume H into delta Z. Delta Z is the this height between the consecutive two passes. So that is also hatch distance we are saying. So that hatch distance is there, and height, and this thing. So this is the travel speed. H is the hatch distance and delta Z is the melted layer width. So these all things we are calculating for heat input. So this I've already discussed in the last Wednesday lecture. Why basically what CMT is made up of. It is the parent technology is GMAW only. So gas metal arc welding, we already know that the droplet detachment is due to Lorentz forces, but with CMT, it's the term called as cold. It's only fusion welding that is having very low heat input. The only fusion welding in the slot that is having very low heat input is CMT only. The term cold doesn't means it is cold. It is relative terminology given by the company, Fronius company, that is patented. Fronius company has patented this technology in Austria in 2004. So this cold means relative term, like two-third of the heat input with the same process parameter we can achieve, and we can deposit the material. So low thermal heat input is the characteristics, and liquid droplet detachment from filler wire is due to the wire attraction motion for better arc stability. So this is the typical system we are having in Delhi Technological University. This is the CMT machine. This is the wire buffer, torch, fixture, torch traveler. Here we are not using any robot. So we are using a single track mechanism. We can deposit single wall structure easily, multi-wall structure easily. But with the increasing complexity, we can't use this torch traveler. We have to use a CNC setup or this KUKA robots, robots like KUKA robots or Yasakawa robots that we can incorporate in the same machine. Then we can do the circular profile or the hexagonal profile or the intrinsic complex shapes also we can fabricate. So this you can see the CMT oscillatory movement. This is captured by CCD camera. This is not a visually uh, available. Like this is in the milliseconds. So in 1 second, it is uh, retraction is happening around 60 to 70 times. So this is very much recorded by CCD camera only. The CMT process I have told you in the last class that PCP, BCP, and SCP, there's peak current phase, background current phase, and short circuiting phase. Peak current phase um, creates the droplet at high current with a short time, and then the current and voltage has been reduced. Due to this reduction, it prevents globular um, transfer because the liquid is not be the diameter of the liquid metal is not increasing because of the reduced current. So that's why the droplet is attaining that diameter. It is not increasing as compared to GMW process that we will discuss in the current waveform. This is the current waveform of the CMT only. So at the time of short circuiting, you can see um, time of short circuiting, we are having zero voltage. This is having zero voltage. Wire comes in contact with the weld pool, and the traction, this DPC, digital process control, is the heart of CMT that decides at what time the wire has to be retracted at the time of short circuiting. This DPC is controlling the wire, and then the droplet detached and deposited. So at lower heat input, the droplet is detached. So the main difference between GMW and CMT is as we are increasing the current and voltage in the GMW, and Lorentz forces are responsible. But in the CMT, it's advanced short circuiting process. At the time of short circuiting, the current is constant or less as compared to this, and voltage is almost zero to prevent the higher heat input deposition. So that is the major difference, and the oscillation, the liquid droplet is detached due to wire attraction motion. Here, the responsible is Lorentz forces. This pros and cons we already discussed. This burn throughs are there in GMW. Due to residual stress, the deformation is there, cracks, and high spatter, heavy distortion. So CMT carries these advantages: spatter-free, thermal heat input, high gap bridging ability, negligible distortion. You can see in the images. So this is the development of CNC integration WAM system set up using GMW, GTW, or CMT TOR. So this we have developed in IIT Delhi. So this is the CNC setup having four stepper motors, two stepper motor in X direction, one in Y direction, and one in Z direction. So this is the torch implantation. Here we are putting the torch and we are fabricating, and this all is connected with the Arduino through the software. This open build software we are using. With the laptop, we can control the any intrinsic shape. You can see circular shape can be done, rectangular, hexagon also we have made it. So all the things you can just design it. We have to add a shape. This is the process of in this software. We have the adding of shape we have to do. Then select the shape for giving tool path. You have to give the how the torch has to move from the outer shell to inner shell. That tool path we have to give, and then we have to configure the tool path. We have to optimize that thing, and then we have to then the system already is giving the G codes, so you don't have to write any G codes. The system already with the dedicated shape that you give generates the G codes. After generation of the G codes, the G codes are put in the machine, and then the arcing will start, and it will follow the tool path as the direction you have given, that through that G codes, it will trace that path. So it can trace the inner path also, everything we can fabricate. So this is the example of single wall structure. You can see this is very high, less height we have attained. Then the final product is like this. It is almost like 70-80 mm, 7 to 8 centimeter, you can say. So it's a single wall structure. You can see the video. This video is visible?
Yes, sir.
Yeah. Okay, okay. Yeah, you can see the video that how the CNC system, CNC router is attaining the circular shape. So this circular shape you can attain by many segmented, like a circle can be attained by 64 to 128 segments we can make, and we are using here the GMAW process. So average voltage and current we can set. The sparking is, you can see, it's of high thing sparking because of the process. If we are using the same, the holder is same. If we are using this CMT torch in this, then this arcing will be very less, like spatter will be very less. So the machine will be same, but the torch implantation, we can use the tick torch also. We can use GMW torch. We can use CMT torch. So the process will change, but the dimensional accuracy will attain as per this CNC setup. So this, in this dimensional accuracy we have almost zero point 0.2 to 0.1 mm. So that is very good dimensional accuracy is compared to AM process. So this hexagon process we are having, you can see, I think, 1 second, it's not, yeah, now it is starting. You can see the video. You can see the G codes are available. Now it is, the arcing is started, and the torch will trace the path. It will trace the path as per your G codes that you have generated through the software. This is stainless steel material, that is 3308L. L represents the low carbon content. Austenitic stainless steel it is. And this, why this glass wool is here, you may be imagining. This glass wool, 1 second, after the video I will explain that. Yeah, so you can see a red hot stainless steel is here. So for every each layer, what we are doing is we are settling it, solidifying it for 30 seconds, and then the next layer is being implanted, because we are using thermal imaging camera or IR camera you can use to check the temperature profile or the temperature at this bead. So the interface temperature, interpass temperature should be constant throughout the building direction, as we are building from substrate material to up the top surface. So the temperature gradient should not be mismatching, otherwise the anisotropy problem will increase. So this glass wool I was explaining, why this glass wool is here. In the last slide you can see this glass wool. So this glass wool we have incorporated in the torch because at this high temperature, this system, the CNC system is having this thermal sensors, like it can't reach around 400 to 500 degrees Celsius. So this glass wool is protecting this aluminum sheet, aluminum this holder. So this aluminum holder doesn't have that temperature. It can't be attaining because the frame is made of aluminum 6061, that is having a melting point of 650 degrees Celsius. So during welding, it is like temperature is almost 2000, 3000 degrees Celsius. So this glass wool, we are keeping it to protect this temperature thing. So that is the just protecting the aluminum frame. So this we have integrated, that I've told you, that advanced TIG process, everyone is using this. Now Fronius has already has been made into the market, this advanced TIG, and ESAB also, and Ador. These companies have already made in this market. You can see here is the TIG torch. This is the standard TIG torch we are using. But what we have done it, this is the like low cost. You can see we have incorporated this setup, small setup of this automated wire. You can see the wire thing. This is the standard torch. This is the wire that is coming at a 45-degree angle. This is the tungsten electrode, you can see. And this is the fixture, filler wire, and this is CNC head with TIG torch. So how this wire is automated is, we have integrated with a different cold wire feeder. This is the cold extra wire feeder we are using, external wire feeder, because in MIG we are already getting a filler this um, wire feeder, but with TIG we are externally applying this cold wire feeder. So this separately turns this wire, and we can manage wire feed rate with this external cold wire feeder. So this is the CNC controller black box. So now we can fabricate VAM component using this advanced TIG also. So make also we can make TIG and then CMT torch. If we integrate, then we can fabricate these things. We can fabricate a VAM component of different layers. So this is the basic thing, like basic single bead profile. So before fabricating a VAM component, we actually perform layers layers bead on plate experiments, because if we are fabricating a single wall structure or a multi wall structure, we need optimized process parameters for that bead, optimized process parameter for that component. So by checking the process parameters, what we can see, we can alter the process parameter with different heat input. So with a minimum heat input and the maximum heat input, we can make a range with minimum heat input, like how, whether the bead is being deposited or not, and the high heat input means like at maximum high heat input means like what is the, how much thick or how much metal can be deposited. So in that range, we can set the process parameters. We can use voltage, wire feed rate, welding speed, current, uh, gas flow rate, contact tip to workpiece distance, stick out distance. These are the different filler wires also we can use as a process parameters. So we can lay the single beads at different process parameters. Here you can see all the different beads are deposited, and then we are cutting this cross section. We are cutting this cross section. We are cutting this section and seeing through a cross sectional area. You can see. So this is the cross sectional image. You can see the penetration area. You can see the reinforcement area. You can see the contact angle. This is the contact angle. This is the reinforcement height. This is the penetration height. And we can find out the area also to calculate the dilution. That is penetrated area upon the total bead area. Total bead area comes in the combination of reinforcement area and the penetration area. So heat input we can calculate by this, and net heat input ratio we can calculate by heat input upon the total bead area. And this is the weld width. So all this we can do with the ImageJ software. We can find out these um, height, depth, contact angle, and even area we can find out by images software after getting this macroscopic image. These are the macroscopic image of the weld bead. So after attaining the macroscopic image, we can give a scale bar through images software, and after that images software we are using, we can find out the all the bead aesthetic profiles like reinforcement, penetration, contact angle. These things we can find out by images software. So after finding out these things, you can see bead on plate trials. This my student has done it. This is my first PhD student. So he has find out the minimum and maximum current, that is 50, 70, 90, and then set B he has taken. Then travel speed. These are the parameters for heat input. There's a minimum heat input parameter he has find out, maximum heat input, and then he has tried. He has done the hit and trial method, and he has laid over the beads at different process parameter. So at what is the layer aesthetics of minimum heat input, and what is the layer aesthetics of maximum heat input. So 50 ampere and 7 mm per second, that is current and welding speed. So 50 ampere, 7 mm per second, you can see here, there's nothing, no bead has been made. So this is the minimum heat input range that we are observing, and 60 and 8 is also minimum. 60 and 8, you can see here 60 and 8, here also 60 and 8. So this is partial. So this we can check, this we can even consider for a single bead weld, but there's the minimum thing. So maximum thing is 90 ampere to 3 mm per second. Here nothing is there. 104 he has implanted. 104. This is the maximum. So you can see the width of the bead, and you can see here. So by increasing the current and decreasing the welding speed, you can achieve higher heat input as per the formula, because if the welding speed is decreased and in current is increased, the heat input will increase. So these parameters are found out. Then he has done the bead on experiment. He has made a design of experiment of 60, 80, and 100. This is the three levels he has decided, and three levels of welding speed. And this is the minimum and maximum level. And design code is this. These combination are achieved by design of experiment, this design expert software, with using face centered design, CCD design, CCFCD design. It is the central composite face centered design. So in this CCFCD design, the central value means this 80 and 6. This 80 and 6 will repeat almost 5 to 6 times. You can see 86, 86. So central value will be repeating itself 5 times at least. Yeah, it is 5 times in this 13 experiments. So he has done it. All the experiments has been done at different process parameters. So after process parameters, he has uh, cut the plate 1, plate 2, plate 3. This is the cross sectional. This is the small sample preparation. You can see the cross sectional image with the scale bar, you can see. So with the images software, you can find out uh, this welding width, penetration, and deposition. So the by attaining this macroscopic image, how we have, because without polishing we can't get this penetrated area. Just after cutting, we can't achieve this. To achieve this images, we have to follow polishing process. That is all the standard metallographic polishing we can do till 2500 grades, or 4000 also you can use. After that, etching you can do depending on the material. If it is, this is aluminium 5356. So it's aluminum, then we are using Kellar's reagent. If you're using Inconel or stainless steel, you can use Aqua Regia. Stainless steel, we can use Nital. So depending on the material, we are using standard etchant also, and then bead cross-sectional image can be taken. So these are the basic bead terminologies, that is reinforcement area, weld width, contact angle, height, depth, penetration area, and the base plate, substrate plate. So after getting all the inputs, that is bead width, reinforcement, penetration, contact angle, and dilution, so all the values we can put, and the software will be optimizing these things. What is the best combination of these all five things to get a best combination of process parameters for further fabrication of VAM component. This is just the optimization of the single bead component, single bead layer. So if we can optimize the single bead, then we can fabricate a very good VAM component. So just not the hit and trial method is not there. We have to completely do all the things. We have to optimize uh, depending on the criteria also that we have to see in the later slides. So optimization of response, you can see this is the weld width. So this is the first this is the first response width, the reinforcement is second. So first response is weld width. So there's an over table you can see, and you can see the software is giving uh, this we have to check the p-value. If the p-value is less than 0.05, then all the factors are in range or significant. If lack of it is more than that, that is not significant. So these are all significant factors. That is the current, that is represented by A, welding speed, B, then the combination of current and welding speed, then the square of current, then square of welding speed. So these all factors have to be significant to get a then to get a model that is significant and having high repeatability values, high repeatability chances. So this p value has to be less than 0.05. That is, this is p is the probability value, and this is f value is the Fisher value. So f value and mean sum of square values decide the contribution factor. So this contribution is calculated by sum of squares. So um, from the contribution you can judge like what is the dominant factor for this response. So how the weld width is um, responding, or what is the dominant factor by which the weld width can be influenced. So that suppose current, here the value is more, 36.31 percentage, that is the contribution that we have to calculate. So this percent is higher than welding speed. Welding speed is having only 9.13%. So 36.31% represent means that current is the dominant factor for controlling weld width. So a slight change in current value, suppose if 1 or 2 ampere of current has been changed, the weld width will change very drastically. So this is the dominant factor. But if we change welding speed to the small values, weld width may not be changing that much, because current is only dominating this. So that's how we can calculate all the other responses. Um, so this is the model graphs of weld width. You can see this is the interaction curve, this is the contour curve, this is the surface 3D plots, and this is the predicted and actual results. So actual results are like straight lines. The actual results are the points, and straight lines the predicted values, and you can see it is in same line. So the model is significant. And this color representation is done by the intensity of weld. So this red color region and this blue color region represent the values of weld width. This red color region means higher weld width. This is uh, considering lower weld width. So this comes the second weld reinforcement, second responses. So the same thing we can check. These all things should be significant. You can see the p values. Then lack of it is not significant. You can see the contribution. So this time 25.46 percentages is welding speed. So welding speed is the dominant factor for weld reinforcement. So if we are changing welding speed by small values, the weld reinforcement will be changing drastically as compared to the current values. If we are changing current values, that much change is not observed as compared to welding speed. So that we can decide after significancy only. So these are the model graphs of weld reinforcement. You can see the interaction curve, contour, 3D surface plot, and predicted versus actual. So this is the third response, penetration depth. Similarly, here all the factors are significant, and this 29.27% contribution in this current is the dominant factor for penetration. So current decides how much penetration depth can be altered or can be made. So the interaction curve, similarly, we are doing for all the all the responses. There's the contact angle. Here also current is the dominant factor. You can see the p values very less, and current is deciding the contact angle. So this is the different contour, everything that we can plot. So this is the dilution factor. So in this, this is the p values less values of 0.05. So here again current. So current is the dominant factor for most of the responses. Just only for weld reinforcement, welding speed is the dominant factor. So majorly if we are controlling the current and we are optimizing the current values, all the other things can be easily, all the other responses can be easily optimized due to this current values. So this is the model graph for dilution. Wait for 1 minute. So yeah, so this is the model graph for dilution, interaction, the contour, this 3D surface plot, and predicted versus actual. So this is very important. So after doing these all things, we are coming to the criteria section. What is the criteria that we have to set for what output we need? If we are doing only single bead optimization or single bead weld bead optimization, the criteria may be different. But if our objective is to optimize the VAM component, so optimize the weld bead for the fabrication of VAM. So for VAM fabrication, we need weld width to be maximum that we have set, and reinforcement to be maximum. Why reinforcement to be maximum is to increase the height of the component. So as the reinforcement increases, the height of the component increases. Then penetration should be in the range that is 1 to 1.5 according to the values that we have got, that these values have set. So why this penetration should be in range? If it is more than 1.5 and more than 2 values, then the it comes in over penetration. So it should not be that penetration should not be that much. So if it is more penetration, you can observe that um, this 1 second. So over penetration means if we are implanting the second layer, the penetration is more, the inner layer width will be increasing, so that we don't want. It should be in the range, not so much high, not so much less. If it is less than 1 mm, then again one problem will be there of delamination. So both layers should be intact, it should not be delaminated. So that value should be in the range, not so high, not so low. So that you can check. Then contact angle, the target value we have kept at a 90 degree. Contact angle means if it is 90 degree, the surface roughness on the side profile will be maintained constantly. So for after fabrication, you can just do a slicing or the machining process, then you can remove the undulations. So suppose this is the layers. If we keep 90 degree, that meant we can just slice it off all the layers and the final product will be easily we can get. So that machining problem, we can avoid that. Complex machining problem we can avoid. We just have to give a slice on both the sides and we can achieve the bulk component here, this central component. So this undulations, if it is very less, like 90 degree, if we are achieving, then if the undulations is less, the machining will be less. So that we have to keep in mind. Then the dilution similar to penetration, we are keeping in range 15 to 25%. And this reinforcement also we can keep it in range and weld width, depending on the um, combination and what are the values we are achieving and what WAM component, the exact dimensions of the WAM component we have to achieve, that we can take in consideration. Because if the values are in range and you have to extract the other samples also, like tensile and hardness, corrosion samples, so that we have to take in the consideration what are the final dimension of the WAM component. So final dimension of the WAM component should be according to the criteria, then only that thing can be achieved. So this is the optimized parameter that my student has done this. The optimized current, welding speed. This is the width. This is the reinforcement. This is the penetration, contact angle, and dilution. So the desirability is 64.8%. That is the repeatability factor, that we can repeat these experiments at 64% rate. And there are 11 solution, but this is the best solution that we get. So it is almost 80 ampere current and 4.4 welding speed. So that if that we can do. So if final optimization we have to check the confirmation test also. We have to go for confirmation whether these process parameters are giving the same results or not. So that we have to confirm after again doing the experimental tests. So this confirmation table is occurred from the design software, and these observed values are kept vacant because that we have to fill after doing the confirmation test. So like if this is the optimized parameter, we have to set these parameters and we have to lay over the bead the final confirmation test bead. We can do a 3-layer bead and then we can cut the cross section, we can polish it, and then we have to check the responses like width, reinforcement, this dilution, all the 5 responses we have to calculate, and then we have to check whether it is in the range of the software values or not. So if it is in range, then no worries, the confirmation test is done. And if it is not, we have to take an average value. It should be almost this, because the model has also given this significancy. So it will be almost it. It may not be accurate, like it can be 6.31, 6.32. That much error will be uh, taken care of. So this is the fabricated sample from the trial process parameters that my student has done. This is at 60 and 6 ampere, and sorry, 80 and 6 80 ampere and 6 mm per second. Then the sample 80 and 8. This is 100 and 8, and this is 60 and 4. You can observe here. He has started from this position at the start of the experiment, and he has reached to this. This is the final at the top of the building direction. This is the building direction, and this is the top view of the sample. You can see here the problem is there. We are getting the staircase defect. This is called a staircase defect. Staircase. In the later slides, I will be taking like from A point, the starting point, and this is the B point, that the top surface that we have achieved. That is the staircase defect. So this defect has to be removed. This defect can be removed by by correcting the dimensional accuracies, how at what position the arcing has to be started and the arcing has to be stopped. That that consideration we have to take care. So it should not be like this. This is having some defect of staircase, you can see, but the undulations are not that much, so that you can see, like after machining the surface will be very smooth. And in this sample you can see the this sample is having this defect, one defect you can see. And after cutting we can see the porosity levels, or if we can go for topography, 3D topography, sorry, tomography, then we can check about the porosities level at the bulk thing. And you can see this second sample is having this humps. It's like a camel humps, you can see humps, humping. So this is the defect, the second defect that I want to talk about. This is humping defect. So this is common defects that everyone can get, because this is a softer material. In stainless steel or in conal, it may not be that much prominent. But with the softer materials like aluminium, magnesium, these problems will be increasing. Like humping defect is very common for soft material. You can see the humps here at this section. Humps are there. So this can be removed by lowering the process parameters, lowering the heat input. So it is 80. The current is 80 and speed is 8. So if we can reduce the current values, then we can achieve a very good straight bead or straight VAM component. And similarly, this 808, you can see here also the staircase defect, small problem is there. It's not that much accurate. And similarly, fourth component is 60 ampere and travel speed 4. So you can see this is a very good VAM component. This is almost 100 component, and the dimensional accuracy is also consistent, and the surface is not that much wavied. So that surfaces, you can simply go for CNC milling, or yeah, CNC milling, you can do it for surface flatness. We can have a very good surface. The width will be reduced and we can extract the samples. So if we are not going for CNC milling, we can extract the sample, then we can go for the polishing process. That because if we are doing CNC milling operations, some stresses will be formed, like some after CNC milling process, some or we if we go for grinding process, if we reduce this waviness by grinding, also some residual stress can be incorporated. So if we don't want these residual stresses to be there, so we can go for the as fabricated cut. So he has done the all the sample extraction. This is the tensile specimen, vertical tensile. This is the inclined tensile. This is the horizontal tensile, and this is the square samples. That is 10 by 10 and this cylindrical sample we can extract for wear specimens, that is 10 in dia. So after extracting this, we can go for polishing of the surface. So by polishing, these residual stresses are not that much the intensity of residual stresses are not that much. So we can get the exact values of tensile strength and hardness values, wear thing corrosion value. So, but if we go for CNC milling and grinding operation, that can cause some, it can cause some like compressive residual stresses also, and tensile residual stresses, we don't know. But if it is having some forming some residual stresses, it can be a helpful or it can be detrimental to the component. So that we have to take into consideration. We can compare the both the samples, like before, like as fabricated sample by polishing the results, and by grinding or by CNC milling, how the samples values are changing. So that can be done. So these are the extracted samples you can see. So this is all study has been done by my scholar. So he's not completed yet, but he will be doing the further tests. So coming to the temperature profile, so that I've already told, from one layer to second layer, what how the temperature can be changed, how the temperature can be maintained. We can use the thermal imaging camera, or in this case I've used both, a thermocouple. I've used K-type thermocouple, and this Fluke TI 400 infrared fusion camera. This is thermal imaging camera. So what I have observed is, laying over the beads, and we're connecting the thermocouple, the values are almost same, the thermocouple values and thermal imaging camera, the both the thermal the values are same at the positions. This is the base metal, this is heat affected zone, this is the weld. So at the central value of the weld, you can see the highest temperature, you can see heat affected zone and base metal. So you can see the temperature profile, how the temperature profile is turning it around, and almost plus minus 5 degree temperature difference is there in the two um process, like thermocouple and thermal imaging camera. This is the main difference, like only plus minus 5 degrees. So this is, we can adopt these sensors and sensor integration and thermal imaging camera we can adopt. So this paper I have already published, is available in the Science Direct. So this is the control of humping phenomena and analyzing mechanical properties of aluminum silicon wire arc additive manufacturing fabricated using CMT. So basically what we are doing is layering of the aluminum samples at the path, different path strategy. Path strategy is very important if we are going for unidirectional path strategy and bidirectional path strategy. What we have to adopt, so unidirectional means if we are starting from this position and we are going towards left direction, and then the torch is again coming to the same direction without welding or without layering of the bead. So the first layer, how, from where we have started, suppose A point, the second layer is also starting from the A point. So the same point is the starting of the layer, each and every layer as the building direction. This is known as unidirectional. If we are going to the bidirectional, this suppose A point is the starting of the first layer, and this is the B point. Just we have to increase the height. What is the height, the hatch distance we are taking, and we are layering, we are starting the second layer at the different B point, at that is the end of the A first slide. So we are layering of the second slide at point B, and we are continuing through towards A point, and then alternatively you can see the layer can be deposited. So what is the output of this change in direction is, you can see here, this sample is fabricated by 50 ampere unidirectional path strategy, and you can see this is the 50 ampere same process parameter, but this is bidirectional. You can see there is no step staircase defect or the humping defect or the any other defect. This I have already calculated also, porosities are also less. It is almost 99-98% of the commercially available aluminium density is comparable with that. So the we can check the density by Archimedes principle. So we can cut the sample and dip it in the water, and we can weigh that thing. So using the Archimedes principle, we can check the density. So the bulk density can be formulated, and we can compare with the commercially available aluminum alloys. So this is aluminium 4043 alloy 4043, that is aluminum silicon filler wire, that is 1.2 diameter that we have deposited. So suppose we have made unidirectional, bidirectional, and then what I have done it, we have increased that current values. So suppose 50 ampere to 60 ampere, just 10 ampere we have improved, we have increased, and the strategy is same, bidirectional. But still, you can see this is done by CMT process, and you can see the humps, how much humps we are getting in each and every layers. You can see, you can imagine how many humps are there. So these humps will create these aesthetic problem, and the strength related things are also reduced. So this is due to high heat input. As we are increasing the current or reducing the wire welding speed, so as we are increasing the heat input, we can have these humps can be easily detected at higher heat input. So you can see humps. This is the top surface, top profile of the aluminum alloy. This is the top profile of the sample. So comparing these two samples, you can say this is the very good sample that is fabricated. And after this is the as fabricated that we have got, and we have gone through the CNC milling process. You can see this surface is cleaned, and now we are extracting the sample. So after extraction, the same thing that we did is we have to calculate the tensile strength. So we um, extracted horizontal, vertical, and inclined samples through the same specimens, because the ASTM standard E8M we have followed. So we have got the stress strain diagram. It is almost same that like some problem is there with this 60 ampere bidirectional, this blue color, but because of humping defect. But the maximum UTS, ultimate tensile strength, is achieved by 50 ampere bidirectional and 0 degree. 0 degree means that is longitudinal direction. So longitudinal direction, once again. So it's in longitudinal direction means that this thing. So maximum tensile strength is achieved at 50 ampere bidirectional, 0 degree. So in this case, we already know that 60 ampere is having that humping defect, and this is 50 ampere unidirectional. We have seen that cavities been formed. So this is also not good because of the material wastage we are getting. So the strength that is maximum is in the best case scenario, that is 50 ampere bidirectional, and 0 degree orientation, that is longitudinal direction, to it is towards the layers, towards the layering of layers. That, and this should be having minimum tensile strength because it is in transverse direction. It is against, this is perpendicular to the layer, perpendicular to the layer deposited. So that we can check, but still it is not that much thing. If we consider one complete sample, it is like this red color. If you consider this 50 ampere bidirectional, the minimum tensile strength is like this and maximum tensile strength is like this. So it is in range, like that much anisotropy is not there. If it is in range, the vertical sample and the horizontal sample, if it the strength is almost same, or plus minus 10 megapascal are there, then we can justify that the anisotropy, the property here at the lower, this is the base, this is the substrate metal, and the property at point A and properties at point B. Suppose this is the B, this is the top surface. So properties are not mismatching because the anisotropy is not that much high, or the we have considered the thermographic properties or thermal imaging cameras. Using thermal imaging camera, we have verified that every layer is having a constant temperature, so that's why that strength related thing is not that mismatching. So the conclusion for this paper was the bidirectional strategy is an effective method for layer manufacturing due to lesser material wastage and higher product reliability. Pumping defect plays a vital role in reducing the tensile strength and percentage elongation. Pumping defect can be controlled by selecting low heat input process parameters, which are easily done by CMT process. So if we are considering GMAW process, humps will be created then because of high heat input. So that we have to take care. So this is another paper that I published. Huh. Is Vishal, whether I'm audible? No?
Yes, sir. Audible, audible.
Yeah, yeah. Okay, okay. I thought I'm just speaking. Okay. So one second. Yeah. So material characterizations is a very good journal. So we have published the title was Influence of Heat Input on the Evolution of Delta Ferrite Grain Morphology of Stainless Steel SS308L fabricated using VAM CMT. So in previous paper I was discussing about aluminium alloys, and this is paper published with stainless steel. So the similar thing we have done it, layering of multiple layers in the single wall structure and then extracting the samples. And then after the microstructural extraction, you can see. So main novelty of this paper was like we have taken SS308L, that is completely austenitic stainless steel wire, that is austenitic stainless steel wire of 1.2 mm diameter. But after layering, like after layering the first layer and then second layer, multiple layers that we have observed, and then we have cut the sample and checked the XRD. So what XRD is showing is it is not completely austenite. So some formation, this is the austenite, you can see three samples we have fabricated, and this is low heat input, medium heat input, and high heat input. This is three XRD graphs you can see, and the heat input values are visible here: 234 joules per mm, 369, and 643. So different heat inputs we have checked the XRD. You can see this box is gamma austenite, and you can see some traces of delta ferrite also. So how this is happening is by depositing austenitic stainless steel, and when it is in the solidified form, some traces of delta ferrite is also included in the structure. So how you can justify this is uh, that when we are melting the austenitic stainless steel, and when we are seeing the iron carbon diagram that everyone knows about that. So at low carbon percentage, that this we have taken L means that is low carbon percentage, that is less than 0.03% percentage of carbon is used in this stainless steel. So as we are melting the austenitic stainless steel and depositing and then solidifying it, so some traces of delta ferrite that is formed at the top of the um, temperatures, like almost 1300 degrees Celsius to 1500 degree, sorry, 1100 to 1300 or 1400 degrees Celsius, that delta Fahrenheit is formed, and then it is retained at the room temperature. So it is not completely austenitic. Some traces of delta Fahrenheit is retained in that matrix. So that you can see in the microstructure, and that we have justified also. So you can see the microstructural images of this deposited samples. So this is the micro inclusion. This is just a one particle. This gray portion is the gamma austenite, and you can see this grain boundaries, a black color region is delta ferrite. So there are many, it's a like pool of gamma austenite and delta ferrite. So much percentage is there. So we have calculated this percentage using this ferritoscope. This is known as ferritoscope. This calculates or measures the exact percentage of delta ferrite in any of the austenitic samples or ferritic samples. The ferrite percentage can be calculated using this ferritoscope. This ferritoscope is based on magnetic induction process. So as we already know that austenite is non-metallic in nature and ferrite is magnetic in nature. So what ferritoscope do is it checks the magnetic particles, the magnetic particles, and it is based on magnetic induction. So how much percentage of magnetic particles are there, that is um, justified as the ferrite content. So ferrite content, we have to just this is the probe of the ferritoscope. We have to just touch the sample on I have taken on the cross-sectional surfaces. This is the cross-sectional part. So cross-sectional surfaces, I've checked this ferritoscope, and the values are there in the ferritoscope. You can see the values. This is for maximum heat input, and this is for minimum heat input. The same thing. And you can see the delta ferrite for maximum heat input is almost 13%, like 12.89% plus minus 5.55. And gamma austenite is the rest over, like 85.33%. Micro inclusion is less than 1.55. So with low heat input, you can see the delta ferrite values are almost 8%. Gamma austenite is 89.68% and microinclusions are less than 0.36%. So by conducting this ferritoscope test, we have observed that with lower heat input, the delta ferrite is less, and we are increasing the heat input, the delta ferrite is increasing. So by increasing the heat input, delta ferrite is almost increasing, but it is the this is the maximum point of ferrite readings. Like many researchers have already published, like at an average it is almost 10 to 12%. 10% is the average of the ferrite content that is there in the austenitic matrix or austenitic stainless steel using a VAM process. So that we have already measured and calculated, like 8% from the low heat input and almost 13% to the, so an average 10% inclusion is needed. So what is the advantage of ferrite in the austenitic matrix is when we are going for this um, boiler industries, there we use this ferrite percentage as an advantage to the specific application. In the boiler industry, it is needed that 10% or 8 to 10% ferrite should be there too, because it can prevent transgranular corrosion and this SAC corrosions. So the corrosion part has been reduced by this uh, ferrite content. So if it is completely absent, then it is problem is there. So so the inclusion, the automatic inclusion is having a advantage also. So that we have justified with the ferritoscope and the microscope structures, both are giving the same results. So this image, you can see this the average grain size as per heat input and the micro hardness. With low heat input, medium and high heat input, as we are increasing the heat input, the average grain size is increasing. You can see the black color line. Heat increasing the heat input, we are increasing the grain sizes been increased, and the similarly hardness has been reduced. So there is a relation between the hardness and the grain sizes. It is like we already know it is a Hall-Petch relationship. So it is the grain size and is inversely related to the micro hardness or yield strength. You can check about the Hall patch relationship. So as we're increasing these characteristics we are observing. So this is the cross-sectional image of the uh, this part. You can see this is the fabricated layer. This is also, and this is the inner layers, that is the interface zones or HZs. So this and this and this. So if we are laying 1 2 3 4 5 layers, so four inner layers are being observed. So in every adjacent interlayers, one inner layers will be formed. This is very weak portion that I have already discussed. The strength is very less, but we can alter this thing by heat treatment process or keeping the temperature constant during the fabrication process. So these are the typical optical micrographs at different process parameter, different heat inputs and different locations also. So we have found out six kind of delta ferrite morphologies. This is lithiferrite, vermicular ferrite, columnar ferrite, serrated ferrite, globular, and acicular. So these six ferrite morphologies I have discussed in this paper. How this is in influencing the microstructures. What are the shapes of the micro morphologies? So that things. So you can see the phases. This is the delta ferrite here, and you can see the percentage that we have marked here. So almost 7.5 to 13% we have increased the ferrite content as per increasing the heat input. And we have done the pie chart, pie diagram I've made for different morphologies of ferrite. So you can see the red portion is giving the vermicular ferrite region. So red vermicular ferrite is increasing as we are increasing the heat input. This is for low heat input, this is for medium, this is for high. So as we're increasing the heat input, vermicular ferrite morphology is increasing, and comparatively this black is the lithiferrite. Comparatively lithiferrite is reducing. So vermicular ferrite is increasing as increasing the heat input. So that we can justify with the optical micrographs or FESM images. So these also, this is the image threshold graphs. So what this is explaining is how much percentage of ferrite that can be calculated using micrographs. So I have done with two processes, like ferritoscope I have used, that is also giving the almost same results. And with the micrographs, the threshold images, using threshold images, I have calculated the ferrite content, and it is also giving the same output. What is the ferrite content in the each microstructures as per the heat input. So element analysis, we have done different points. What are the elemental mapping, area mapping, line mapping, everything we have done to justify the micrographs. So for further, like, conclude, you can see that weight percentage we have given. So for delta ferrite, you can see chromium is 22% iron and nickel. And for gamma austenite, you can see the percentage values. And so as we are increasing, transforming from gamma austenite to delta ferrite, so chromium percentage is increasing. The chromium is the dominant factor, that is the in improvement of ferrite content. Okay. And this graph also showing the same thing. Chromium is the black region. So higher concentration of chromium, concentration is more, then that means the ferrite is there, ferrite percentage is there. And you can see nickel percentage is reduced. So you can see nickel percentage. So that means austenite phases are there. So that is the significance you can check. So this paper conclusion was like each layer is having two interface zones that we have discussed on the either side. In the fusion line, only globular. So this fusion, this inner layer zones, only few globular ferrite morphology exist because the bigger grains are there in the um, this part. Bigger grains are there in the this inner layers. So we can check the hardness also if the hardness was less at the inner layer as compared to the interlayer. So that we have justified with that. Whereas this at the center of any layer or only lithium and vermicular ferrite was detected. So as the heat input increases, gamma austenite concentration decreases and delta ferrite and micro inclusion increases. So that we've discussed in the graphs. With increasing heat input, Lethi ferrite transforms. As we are increasing the heat input, Lethi, we have talked about as we're increasing the heat input, Lethi is reducing. Lethi ferrite percentage is reducing. That is, uh, they are transforming into faceted morphology, while vermicular morphology is converted into globular ferrite morphology. So as we are increasing it, so vermicular is transforming into globular. That is detrimental to the mechanical properties. So we have to keep the heat input in the limitation. We don't have to increase it too much so that globular ferrite morphology increases and the um, mechanical properties or strength related data will be reducing or ductility can be increased. So that we have to check. So grain growth occurs as a result of vermicular ferrite morphology transforms into globular ferrite morphology, decreasing the micro hardness at the fusion boundaries. So grain boundaries patterns repeats itself. So every layer is having the similar grain structure. This is also known as the this grain morphology pattern repeats itself for each layer moving along the building direction, resulting in repetitive heterogeneous grains morphology with nearly identical chemical composition. So the term heterogeneous grain morphology is related about the how how the different morphologies are present in one microstructure. Like six types of morphology are present in the microstructure is heterogeneous grain morphology in the each layer. So if we go for heat treatment process or quenching process or microwave heat treatment, everything we are doing, so to improve the homogeneity. So to get the homogeneous product, we can go further for post-processing processes, and we can we can find out the homogeneous component. Homogeneous we can develop. So this is the wear characteristics of the same samples 3SS308L. So this I'm skipping. This is just the tribological testing that we have done on the same samples. So yeah, this is the important concept that recently we have published. Uh, One of my friend, uh, uh, Dipin, and I has fabricated, and my professor has been so generous that we have done the collaboration on this joining of WAM component by diffusion bonding. So he is diffusion bonding expert and I have done WAM component. So we have integrated these things. So the application of joining of WAM component by diffusion bonding is there in heat exchangers. So in the complex shapes, these can be fabricated easily. So, in this topic, in this research, nobody is doing till now. Like only our research papers are there. So, if the researchers are willing to do this kind of research, that you can do it by joining a WAM component by diffusion bonding. You have to first fabricate like this our student has done it. So fabrication of SS stainless steel and aluminum alloy of the WAM component we have fabricated, then microstructure and characterization of the single wall structure we have done it. Then by extracting 10 mm by 10 mm sample from the WAM component, and then we have diffusion bonding the same component of that, and then we have checked the mechanical strength and mechanical microstructure properties, and it has found out that using a similar similar metal bonding, like stainless steel to stainless steel and stainless steel to aluminum also, the strength is very good. So we can opt this technique for if we are fabricating an intrinsic shape for heat exchangers, we can fabricate a VAM component and we can join with the similar or dissimilar material using diffusion bonding. So this is the standard bonding process that we use. Vacuum assisted or without vacuum also we can do it. So this is the fabrication process, microstructure process. This is the diffusion bonding setup, and this is the mechanical characterization. Like our student has developed a die, and using that lap joint, we have checked about the shear strength of the bonded sample. So that is how we have checked the mechanical properties. So this is the same setup that is developed in IIT Delhi. GMW machine, 3D manipulators, argon gas cylinder, microcontrollers. This is the VAM setup. This is the different two materials that he used, ER308L and aluminum 5356. So this is the weld torch assembly. This is the fabricated aluminum alloy and stainless steel alloy. So how he has reached, because we have to optimize the weld bead. So he has done the optimization of weld bead also. Micrographs, we have taken the processes. Then only this best combination has been made. So you can see there is no staircase defect, and the humps are also not there. So you can see it is a very good single wall structure. So uh, it is not fabricated by hit and trial method. We have to optimize the weld bead. Then only we can get the best process parameters to get this final product. So doing the mechanical characterization, we have done the mechanical characterization of the single wall structure. We have taken the tensile specimen at 0 degree, 45 degree and 90 degree. We have checked the strength values. So in this case of stainless steel, diagonal inclined specimen is having a more strength, like 629 megapascal he has achieved. The tensile test was carried out by 0.1 mm per second strain rate, and longitudinal specimen, that is in 0 degree arrangement, that is having 541 megapascal, and transverse is 523. So it can be possible, like the maximum strength can be attained by longitudinal or the diagonal, because the it depends on the porosities also. If the porosity is high in that region, then the strength will be reduced. That we have to check with the Archimedes principle, or we have to find out the porosity at the specific location, so that we can justify with that. And then micro hardness, and these results are there in microstructures he has taken out. So this is all about the VAM process. Then how VAM process has been joined with the diffusion bonding is, we've taken the diffusion bonding machine, that is control panel is here, hot chamber, inert gas cylinder, this is chiller. So this is the internal box inside the chamber. This is the graphite die, upper die, lower die, and this is the sample we have kept. So our first experiment was not successful. So we have to learn from the failures that we have got. So the main reason of this first component failure was fabrication of aluminum alloys using GMAW setup. So I've already told about the, like, if aluminum alloys, this aluminum alloys, how we have developed. You can see this staircase defect is there. Much porosity was there in this component. So this is fabricated using GMAW process with VAM, and this aluminum alloy, after cutting, we have seen there are many porosities. It is like the diameter of porosity is too much big. So you can visually see the porosity level. So that's why after keeping it like in the furnace, in the diffusion bonding setup, that one side we have taken SS308L, and the other side is we've taken aluminum alloy 5356. After diffusion bonding, and this is the diffusion bonding parameters that we have used. Heating the furnace about 550 degrees Celsius, because we have to check the melting point of the aluminum is 653 degrees Celsius. So by hit and trial and the extensive literature survey, we have um, found out that 550 degrees Celsius at this temperature, at this time, it is safe to do the experiments. So 550 degrees Celsius and for 90 minutes, and then holding time we are keeping for 75 minutes at the same temperature, and then cooling in this furnace cooling only we are doing in the ambient temperature. uh, from 550 degrees Celsius to ambient temperature, it is reaching the ambient temperature at the furnace cooling itself. So, what we have found out that the our sample was distorted in the first trial of the experiment. So, because the only aluminium part has been distorted, you can see in the image. SS308L is the same as we have kept, that is as fabricated. After polishing it, we have to polish the faying surface, and then only we can align it, and then we have to keep the sample. So this aluminium sample, you can see it is distorted because of high porosity level. So that is the concept, that is the cause of our failure. So the same experiment that we have done with aluminum 6082, then it is a rolled sheet. This is the additive manufacturing sample. This is 308L, and this is commercially available rolled sheet, 6082 aluminum sheet that we have taken for the trial purpose, whether aluminum and stainless steel can be joined or not, that we have to check with the diffusion bonding. So one sample we have fabricated with VAM, and this is commercially available sheet we have taken, and we have polished it. The fang surface is polished, and then we have attached, and then the component was very good, and we have achieved a very good bond. We have thrown the sample also, it is not like broken. And we have tested this also with chemical spectrometer and this XRD, EDEX, EBAM, like EBSD, everything we have done. So the results are impressive, and that we have published. So this is the trimetallic, like aluminum 5356, SS3008 and 6082. So this we have just tested. So this was not important, only this sample was very good. And you can see how mechanical characterization that we were checking by we have fabricated the die, and what it is like, the upper die and lower die is having the grooves, the 10 mm grooves were there, and we can set our sample at the lap joint, and then we can go for shear strength calculation. So shear strength data is there. So we have got a very good shear test was done at 0.5 per minute strain rate. Average shear strength was 158 megapascal. So gradual drop after reaching maximum shear strength. Micro hardness measurement at 200 grams was done at the dwell time of 10 seconds. So micro hardness was 101. So all the mechanical properties were very good. So then we went for FESM analysis. Then you can see 308L and 6082 here. By seeing the FSM image, you can see the porosity levels are very less, and you can see this is the bond line. This white region is the bond line, and we have seen that diffusion bonding of VAM sample of SS and aluminum carried out successfully. Bond line are free of porosity, voids and cracks. EDS uh, carried out to find the elemental diffusion across the bond line also, like line mapping we have done, area mapping we have done. So every characterization that is possible we have done it. So intensity of constituent elements has gradual drop. Whitish layer, you can see here some white layer is there. So white layer observed a diffusion of possible formation of intermetallic compounds. So bonding between stainless steel and aluminum causes some intermetallic compound because of their different thermophysical properties. So that intermetallic compounds also have has to be in the limits, like within the 10 microns width, so that to keep the bond strength at the up to the mark. Otherwise, if the intermetallic components width, IMC width, is more than 10 microns or 20 microns, then the problem is there for bond strength. The bond strength is not too much high, so that we have checked. Then SEM images revealed voids and porosity in this, that I have already told. The failure of our first experiment 5356. So due to that SEM images, these higher porosity levels are have we have visibly we have checked, like due to these porosity only this deformation has been taken place. So presence of voids near the bond line weakened the joint strength. So if the bond in the during the joint strength, the bond line should not be having any porosity or the voids, so that should not be there. So EDS analysis explains all the characterizations. This EDS, you can see the chemical compositions and all. So we have done EPMA also. EPMA gives the exact percentage of the elements. EDS is not that much accurate as compared to EPMA. So if the atomic number, if we are finding out nitrogen and oxygen and carbon, like if the atomic number is less than 10, you can go for EPM analysis, because EDS will not give the exact percentage of the low atomic number elements. So if we are finding out the low atomic number elements, so we can go for EPM analysis. So this is quantitatively and qualitatively both results it will give with the line mapping and area mapping. So it is very correct method for the less atomic number elements. So we have done with similar materials also. Aluminum, stainless steel we have already done. So SS to SS we have bonded. So the temperature, the process parameters are different for this experiment. That is heating about 1000 degrees Celsius for 150 minutes, and then holding for 65 minutes at the same temperature, then cooling at ambient temperature, that is furnace cooling. So this is SS to SS bonding. So both are additively manufactured. So this is not commercially available SS. This is both AM fabricated, that is wire arcade manufacturing sample through GMAW process. So these both are AM samples, and then we are bonding it to get the higher bond strength. So we can go for similar and dissimilar materials also. So this we have done it, microstructure and EBSD, EDEX, everything. Then this is the component used in naval process. One Navy officer was there to help us. He was a sponsor student, so he was fabricating some circular walls and joining of DB using wire arcade manufacturing. That is also successful. So this we have done it. This is bottom part is stainless steel and the top part is aluminium. So it is not, it's a circular thing, not a normal thing. So observation and discussion we have already told about. The tensile strength was this. FSM results were the bond length was free of defects, porosities and all. So the same thing, I don't want to repeat it. So this sensitization. So sensitization is a major problem in stainless steel. It is the one of the corrosion mechanism which cause widespread problem in austenitic stainless steel, particularly in the welded assembly. So this if we are fabricating SS stainless steel, we have to check, like we have to see that sensitization should not be there. So what is the sensitization problem, how we can avoid it, that is the major concept if we are using stainless steel. So if we are doing this stainless steel fabrication, uh, some carbide formation can takes place, like this M23C6 metal carbides are there, that is formed in the adjacent of the grain boundaries. So this is the grain boundaries you can see, and this is the localized grain boundaries, and this is the carbon concentration, and you can see there is a dip at both adjacent side of the grain boundary. So this is the grain boundary, and left and right both side grain boundaries, both side of the grain boundaries, there is a carbon depleted zone. You can see, sorry, chromium depleted zone. You can see here. You can see chromium depleted zone you can experience adjacent to the grain boundaries. You can see 18% of the chromium, and here you can see 12%. So this dip is there. So adjacent to the grain boundaries, chromium depleted zone will be formed. Why? Because at the grain boundaries, we are adjacent to the grain boundaries, we are forming chromium carbide formation is taking place. So as the chromium carbide formation, the precipitate of chromium carbide occurs primarily at austenitic grain surfaces, which are heterogeneous nucleation site. It can occur at in a matter of minutes at temperature around 750 degrees Celsius. So during fabrication, if this problem occurs, like chromium carbide formation is taking place and adjacent to the grain boundaries, the chromium depleted zone is there, then the sample is like having can have a problem of this transgranular corrosion. So that corrosion we have to take care. So that is the sensitization problem. The resulting chromium depleted zone at the grain boundaries makes them susceptible to intergranular corrosion. This is the essence of sensitization. Sensitization leads to the phenomena of weld decay. Regions are created in the heat affected zone at the welds, which precipitates carbide because of because sensitization and fail by localized corrosion. So how we can reduce this sensitization is, first option is to use the low carbon content stainless steel. So how we can use it low carbon stainless steel is that we have used in our experiment, that is 308L. So if we use 308, the tendency of this intergranular corrosion can be high, but what we are using is 308L, so that is low carbon content. So as we are decreasing the content of carbon, so that chromium carbide formation will be the tendency of formation of chromium carbide will be less. So as the tendency is less, so the sensitization problem won't be there. So this is the first solution, and then second solution is what we can achieve. We can use titanium, this titanium as a solute, or other solute like one second, yeah, we can use other solute as niobium, titanium, vanadium, and tantalum. So these solute, how we can add as a we can add as a solute. uh, why we are adding these things is, these are having greater affinity towards the carbon molecule. So before formation of chromium carbide, these things can be connected to the carbon molecule, and the tendency of chromium carbide will be deleted or mitigated. So there are so these are having higher affinity towards carbon as compared to chromium. So these will bond quickly as compared to chromium carbide. So there are stabilized materials also available in the market. Stabilized stainless steel, that is 321, you can see in the market, that is titanium stabilized. They have used titanium solute, so that you can use directly to reduce sensitization. And 347 also you can use, that is niobium stabilized austenitic stainless steel. So these you can see use through directly towards the fabrication of the wall. Or otherwise you can use 304L and 316L, the L part of the component, that is reduced carbon content. So this is the basic Schaeffler diagram. We can measure nickel equilibrium equivalent and chromium equivalent. We can check what is the combination of the percentages there. We can find out what is the phases formed: austenite, austenite martensite, martensite, ferrite. These formation we can check. So these are the advantages and challenges in the VAM process. There's the basically in the first or second slide I've talked about the powders and wires. So in the laser powder bed fusion, powders are used. So that is very costly as compared to the wire. So that's why laser equipment itself is that much costly. It is around 1 crore, 1.5 crores. So laser powder bed fusion is the machine is on already costly, but the material that raw material that we are using, it is laying over the powders, that is high content of powders. So high quantity of powders we need. So the cost of powders you can see here, it is around in terms of wire, you can see 180 to 1300 rupees per kg for steel and 9,000 to 22,000 per kg for titanium. This is the wire cost. And for powders, it is 5,000 to 8,000 rupees per kg in the case of steel powders, and it is going towards 68,000 per kg for the titanium powders. So work is not done with the 1 kg of powder, so we need a multiple like 5 to 10 kgs of powders for a single component fabrication. So this much powder cost is too much for fabricating a single component, that is a small component or that thing. But the precision is good, but the cost of material is too much expensive as compared to wire cost. So VAM process were cost efficient than the powder based AM techniques. So here I've seen the challenges, the staircase defect. We have already covered this, how we can improve it. That also we have done it. So if we are like, this is important in terms of multi-track, multi-wall fabrication of component. So if we are doing multi-track, this is multi-track, one layer, two layer. This is the adjacent layers we are laying off. So how much overlapping we have to do? So to um, get the efficient bead aesthetics and the efficient multi-track, multi-wall thing, we have to optimize these things. This is very important. So what is the overlapping area we have to do? What is the area of valley? So to attain, we don't want this thing and this thing. We have to, we want this as a final output. So see, so C, you can see C part, that is D less than W. D is the center distance and W is the bead width. So if the center distance is less than the bead width, so overlapping area equal to the area of value. So the area of overlapping and the area of value, we have to be keep it as equal. So if it is equal, then the perfect overlapping can be done. So we have to optimize the weld bead, and then we have to check how much distance we have to overlap, and that area should be almost same. Then this profile can be achieved, and the perfect this multi-wall, multi-track can be formed. So this is the defects associated with VAM. Process related is inhomogeneous residual stresses. Material related is solidification, cracking, porosity. Uh, how we can give the solution as post heat treatment, work hardening, tailoring, cooling rate, nanoparticles use. So residual stresses can be reduced by post deposition heat treatment using perfect jigs and fixtures, and follow proper deposition pattern. And solidification cracking can be tailored by cooling rate, low heat input, compatible alloying element, proper shielding, cleaning. So these all can are the possible solution for aluminum alloy defects. So these are the defects: residual stress, porosities, cracks, and delaminations. And isotropy I've already discussed. These are the cracks. So how we can improve the WAM component, I think the time is over, but uh, in the brief, I can tell you how the quality of WAM can be improved. It is by post-heat treatment, near immersive active cooling, interpass cooling, interpass cold rolling, hot forging WAM, and ultra cold WAM. So these are the six possible solution that after fabrication, how you can improve the WAM quality. So post heat treatment, everybody knows about how the porosity level can be reduced. You can see this is high porosity, which is as fabricated, and after post processing, you can see the porosity level is very less. So as the porosity level is less, we can have a good mechanical strength. Then the second is near immersive active cooling. You can see this is the natural way of doing WAM. Then the passive way, then the NIAC. A passive way means that the fixed level of water is there inside the stand, and then you are fabricating. So this cooling liquid, this cold water, will be maintaining the temperature of the substrate, so that you can make it. And then near immersive active cooling is, as we are increasing the height of the WAM, then the coolant, the liquid level is also increasing. So we are maintaining the temperature to be very much at the same rate, so that cooling of layers, with sudden cooling or quenching, you can say it is also like quenching. So sudden cooling will give the equiax grains, and then we have a good mechanical properties. So interpass cooling, the same setup we are using, and then CO2 gas bottles are used in the 45 30-degree angle, and then CO2 is being pressed during the fabrication, and we are cooling the layers at the time of fabrication. So that will help in like sudden cooling, improving the cooling rate, and then we can have a very good improved strength and hardness. Less oxidation can be achieved. So this is interpass cold rolling. So interpass cold rolling is the, like, the setup is there. This is the MIG torch, and the torch is attached with the roller. This is a big heavy roller. So heavy roller, why heavy roller is needed? Like the profile of the bead is like this, the curvature bead thing. But if the heavy roller is coming, then it is flattening the weld bead. You can see this is the as fabricated, and this is the um, cross section view of the bead after the cold rolling has been done. So it is like a forging process. So as fabricated wall is being made, and then roller is going through point A to B, and then you can see the cross section will be like a flattened bead. So it is like a strips, you can say it is forming a strip. So this is helping in the grain structure refinement also. It's like a forging process. So a hot forging WAM process is like, in during the torch itself, we are using a hammer. So by fabricating the WAM product, by layering the weld bead, we are hammering it. It's a forged surface. So by hammering it, what we are doing, it is similar to this interpass rolling. Here we are using the heavy roller. Here we are using hammer. So by hammering, what the grain refinement can be happening, and the strength can be improved. You can see with 55 Newton hammer, the stress, the strength, UTS has been improved. Like it is almost more than 600 megapascal. And initially it was like 580, 550, and around 500. So 100 megapascal strength has been attained by this. So as fabricated and 55 Newton hammer. So this is the last process, ultra cold WAM. You can see here, the electrons flow we are regulating. The molten pool width has been reduced. You can see. So it's a bypass wire feeder. So we are using a wire feeder here, and we are controlling the molten weld pool. So molten pool, if we are reducing, so it is reducing the heat affected zone, and it is attaining the cooling. It is increasing the cooling rates by 11 degrees per second, and having a significant microstructure development. So these are the conclusions of PPT, like for our presentation. So that we have already discussed. VAM process is successful fabrication of complex product shapes. Large deposition rates with cost effectiveness increases the usage of VAM process in industry, and deposition of steel, titanium, nickel, magnesium, aluminum can be done. So VAM automation and modeling advancement improves the process penetration. The VAM is process and subsequent process cold working or post deposition heat treatment can be done to improve the quality of VAM. So conventional GMW, GTW, every process has been used for VAM, but CMT has become a popular heat source for VAM process that I've discussed about the characteristics. So integration of materials and manufacturing process to produce defect-free and structurally sound deposited materials remains a crucial effort into future. So these are the key feature references. Thank you.
Sir, there is a query.
Yeah.
Sir, the question is that as you talked about the lithiferrite and vermicular ferrite, so
Mhm.
how to differentiate both these ferrite? At what basis that we can either we can see in directly in the microstructure or there is any criteria? So how we will signify that this is the lithy one and this is the vermicular one?
Yeah. This is a common question, like how we are differentiating between the ferrite morphologies. So if you are taking the cross section and taking the microstructure, you can see the morphology, the design of the microstructure is different. As you are seeing, my vermicular is like a vermicelli. Vermicelli, like you basically eat it, like vermicelli thing is there in for food. So it's the terminology is given by that only, vermicelli. So it is the morphology's design is different. So lithiferrite is like compact lines, and vermicular is like a waviness. So during my PPT, I have shown you. It is. I can show you 1 second. Yeah, here. So here you can see. Uh, yeah. Maybe it is not that much clear. Acicular, you can see lithiferrite are this patterns, and vermicular are these patterns. So you have to identify according to the design only. There is no separate machine to detect the different morphologies. You have to check the best microstructures, and you have to identify how much is vermicular, how much is this thing, that you can check.
So we can decide it on the basis of the previous references work, the previous research work that what particular structure name is given.
Yeah, as per the literature survey, you can check the optical microscope image or FESM images. Then you can see how the authors have given the vermicular, and then you can modify, or you can write about that, the region where the vermicular ferrite is more, the intensity is more. So that you can write.
So there is another question in the chat box. What's long range diffusion in this slide and how by rapid cooling sensitization can be avoided?
What's long range diffusion in this slide? Which slide? Slide number is not mentioned. Long range diffusion. Okay, 1 second. Long range diffusion means maybe he's talking about this thing, the holding time, I think.
In
This thing.
sensitization slide, sir, he is talking about in sensitization slide.
I think sensitization is a different question. So for diffusion bonding, the holding time, 1 second, the holding time is this as per the literature, extensive literature survey, we have done it. And we have done some trial test also. If we are keeping 90 minutes and 75 minutes, we have already done some extensive experiments. Then only we have decided these process parameters. And coming to the second question, okay, in the sensitization slide, you're saying, and how by what and how by rapid cooling sensitization can be avoided. Okay, rapid sensitization. 1 second. Yeah, by rapid cooling, how the sensitization can be avoided as the chromium carbide formation is happens at a specific temperature, and it is a slow process. Like it's a this you're talking about, it requires long range diffusion. So that means chromium and carbide molecules to form these chromium carbide, it takes a longer time. So you need that longer time and that specific temperature to bond these chromium carbide. If that one thing is also not there, like time is not there, or the um, this temperature is not there, then this diffusion will not be taking place. So if you increase the solidification rate or the cooling time, if we fasten up cooling, then this diffusion won't be taking place and we can reduce sensitization. So as chromium carbide is not formed, then sensitization is nothing we can observe, like uh, corrosion can't be there. So yes, is there any questions, any other questions?
Participant may write in the chat box for any query. I think, sir, there is no question. So thank you, sir. Thanks a lot for your very insightful views and particular topic over the
Thank
WAM.
you, thank you.
So participant, we will join the next section for at 11:30 after the short tea break. Thank you.
Okay, thank you.